Okay, a new unit. I know a lot of you have been eagerly awaiting chemistry. So this is chemistry for biology, but we have gone a long way in our understanding of the atom through time. So I'm going to try and just give you a little bit of the basics to maybe refresh your memory of some atomic developments you've heard of before, kind of try and tie everything together because this stuff is still changing, just like most of science. It's very true to the nature of science. So here we are. First of all, we're going to start with Dalton. I know atomic notion started long before Dalton, but he was the one that really started looking at atoms, especially the fact that as he studied them, he noticed that during chemical reactions, there always tended to be a predictable ratio of elements by mass. And so that was his major contribution. And then moving on to J.J. Thompson, he used a cathode ray tube to observe electrons and realized that they had a negative charge. He was using a positive piece of metal there to direct that stream of electrons. And so he knew elements were neutral, and so he developed this picture of an atom that you've probably heard of as the plum pudding model. A bunch of negative particles surrounded by a positive kind of cloud or haze. I like to picture this, since we don't really eat plum pudding anymore, it's more like a chocolate chip cookie. The negative chocolate chip pieces surrounded by a bunch of cookie batter, that would be your positive substance to balance out the charge. But this is an outdated model of the atom as well. It's just one that I know most of you have heard about. Rutherford was doing experiments with radioactive material and a stream of positive alpha particles, and when he realized that those positive alpha particles weren't just going through a thin sheet of gold, but also reflecting or bouncing off of it, he deduced that there had to be a distinctly positively charged, or a distinct positively charged particle, not just this haze of positive kind of pudding or cookie batter surrounding a bunch of negative electrons. So if you look here, that was his actual experiment, and then if you look deeper at the gold, that's what's going on inside the foil. So you've got these positive alpha particles, and sometimes they're reflecting off or refracting off, and sometimes they're deflecting backwards, bouncing directly off something else that was positive. That clump of positive particles is what we now know as the nucleus of an atom. And Rutherford was also the one that gave us the notion that electrons orbit the nucleus, that they're not just sitting motionless in a plum pudding. So we still have that notion of orbits now, but it's changed quite a bit. So here's the basic Rutherford atom. And this is a good place to just point out the three major subatomic particles, the electrons, the protons, those that were discovered very early on, and then later the neutrons were discovered. They were a little harder to pin down because they were neutrally charged, or they were neutral. They didn't have a charge. So very difficult to detect those compared to the other two. Protons and neutrons, we now know, are held together by something called strong nuclear forces. And then the electrons are located outside of the nucleus, and we now consider them a part of an electron cloud, not an orbit like we think of the planetary orbits. But they are attracted to the positive charge of the nucleus while being repelled away from other electrons. So again, we got the positive protons and the neutral neutrons being held together very, very close together in a tight nucleus because of those strong nuclear forces that you'll learn more about in physics and probably chemistry as well. This is a table showing the relative masses and charges of those three essential subatomic particles. Now, I don't know about you, but I have a hard time grasping differences when numbers are being carried out to the negative 24th exponent. But if you look here, those are very, very tiny numbers, but you can still look at, the atomic mass units and get a sense that this is about 4 or 5 orders of magnitude different, that the electrons are very, very small compared to the protons and neutrons. Well, how small are they? Well, let me give you a physical, real-life example of 4 to 5 orders of magnitude. That's the difference between the weight of a paperclip and a medium-sized puppy dog. So if you've ever picked up a puppy dog, and who doesn't want to pick up puppy dogs, that's the difference. So the weight of a paperclip is so insignificant to the mass of, something that's about 20, 25 pounds. So that's why when we look at the atomic mass, we just consider the protons and the neutrons. And then every element needs to be identified from atoms of other elements, and we are able to do that with just the protons themselves, the number of protons. So that helps us tell atoms of different elements, apart. Using atomic number and atomic mass, we can also distinguish between isotopes. So isotopes are the atoms of the same element that have different numbers of neutrons. So we've got all kinds of isotopes that exist in nature, and then we have a variety of isotopes that we can create in the lab. These tend to be very unstable. They fall apart quickly. Most of the ones available in nature are a bit more stable. And these naturally occurring isotopes exist in predictable ratios. So you know that you could always have like 91% of one isotope and 9% of the other. So when you see the atomic mass written on a periodic table, you're actually looking at the average of all the isotopes found in nature and their relative abundance. So when you look at hydrogen here, it's very, very common to find hydrogen isotope 1 in nature. It is much, much less likely that you're going to find hydrogen isotope mass 2 in nature, and even more rare to find 3. So these 3 isotopes of hydrogen are the 3 found in nature, although there are some created in a lab. Hydrogen is the simplest atom we've got, so with only 1 electron. So we've studied it a lot. We know a lot about its isotopes, and so that's the only atom that has isotopes that still have common names. Hydrogen 1 is the most abundant. Hydrogen 2 is called deuterium, and it is not radioactive, but it is heavier than hydrogen 1 because of that neutron. So you can use it as a chemical label sometimes, or it is used as a component of what's called heavy water to cool nuclear reactors down. And then hydrogen 3 is a radioactive isotope, so it's going to emit radiation, and it's used along with hydrogen 2 in fusion experiments. This is all FYI, but hydrogen 2 with hydrogen 3 can decay to helium 3, just hydrogen 3 can decay to helium 3 in a half-life of 12.32 years. So all of this, because isotopes are not a major component of our class, as you can tell as I'm stumbling over my words here, all of this is to lead you to radioactive or radiometric dating, which does involve radioactive decay. So really quick about radioactive decay. This happens when nuclei are unstable because of those extra neutrons. And so there's 3 common types of decay. You can look into them more if you want to. They are alpha, beta, and gamma. So different things are being emitted in these different kinds of decay. And the isotope continues to decay until it reaches a point where it's a stable nucleus. Often that nucleus is a nucleus of a different element. So using half-lives, we can track radioactive decay. So given any sample, half of the sample is expected to decay in 1 half-life. So carbon-14 is a radioactive form of carbon used in radiometric dating. It has a half-life of 5,730 years. So approximately 1 in 1 trillion carbon atoms in a living thing is carbon-14, and the rest tend to be carbon-12. So say there were 1,000 carbon-14 atoms in a living thing when it died. After 5,730 years, we would expect there to be 500 carbon-14 atoms. And then after another 5,730, 250. And then again, 125 carbon-14 atoms, another 5,730 years later. So there we go. So that also can be looked at as half, a quarter, an eighth, and a 16th of the original amount that was present in your sample. You can also do this with that original ratio I mentioned, so 1 out of 2 trillion, then 1 in 4 trillion, then 1 in 8 trillion, and so on, 1 in 16 trillion. So that is how we are able to use half-lives of various radioactive isotopes to help us date once living organisms. And so we have a lot of different tools we can use now based on the approximate age we think something is, where we found it, what layer of rock we found it in, and we can date those rocks pretty precisely now with the tools we have to look for these isotopes.